Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to just kind of overview the course so far and talk about some of the things that we've hopefully learned about and how they kind of connect together. So the first part of the course is about the study of motion. And I like to summarize that with a velocity graph here. And that's mainly when we talk about motion, that's usually how I teach people to try to study motion, by drawing a velocity graph and using it to calculate quantities. So here's kind of a generic velocity graph that I've drawn here, where this particle has this velocity at some time and some other velocity at another time. Then this time difference here, that's what we would call a delta t. Two important properties of this graph. First, slope. Basically, the slope of this line gives what we call the acceleration. Right? That's delta v over delta t, and that describes how fast the velocity is changing. When your slope is positive, maybe something like this, that means your velocity is increasing. Negative slope, like I have shown here, would mean your velocity is decreasing. Horizontal slope would mean your velocity is not changing. Once we have a velocity graph, we can use it to calculate displacements. Mathematically in physics, we usually call that something like a delta x. And your displacement is given by area. In this picture, that'd be this bound area right here. Now, in a lot of the problems we look at in this class, there's three real common cases. And if you give me a moment here, I'll kind of overview the three common cases. All right, so case number one might be constant velocity. If your velocity is constant, then this graph would be horizontal out to some time. And then this area would give you the delta x, and the acceleration would be 0. Another possibility is an object whose velocity is increasing. Now I'm going to do this assuming it's starting from rest. If an object starts from rest and its velocity is increasing, your graph is going to look something like this out to some time. And again, the slope would give the acceleration. This area would give your delta x. Another common case we've looked at is an object decreasing in velocity. So I'm going to assume that this starts out at some positive velocity, whatever that is. Maybe we'll just call it v sub o, and we'll look at what happens when we bring that object to rest. Now we have a negative slope, indicating our acceleration is in the opposite direction of the velocity. And again, this triangular area here would give your change in position. Now, there are there's really an infinite number of possible cases here, but the courses in which case for which I'm intending this video for, these are pretty much the examples that we look at the overwhelming majority of the time. Some other things to consider. Anytime our velocity is positive, the object's moving to the right. Had this curve continued, maybe something like this, this area would give a displacement in the negative direction. All right, let's talk about number 2 here. So the second part of the course is Newton's laws of motion, with the biggest one being Newton's second law, which is net force equals mass times acceleration. It's very important to understand kind of conceptually here how these things fit together. What this equation basically is saying is your acceleration will be large when your force is large. Your acceleration will be small if the mass is large. So acceleration gets bigger with force, but it gets smaller with mass. And being a bit more detailed, this is a directly and inversely proportional relationship, meaning since the acceleration is equal to force over mass, right, directly proportional to force, inversely proportional to mass means basically if I double my force, I'll be doubling my acceleration. If I tripled my force, I'd be tripling my acceleration. Inverse relationships work like this. If I doubled my mass, I would get half the acceleration. If I tripled my mass, I would get 1/3 of the acceleration, and so forth. So at least a conceptual understanding of how these two variables affect this one is important here. Now, what do we use it for, Newton's second law? Primarily for going back and forth between force and acceleration. I mean, sometimes there's going to be problems where we're given the force and the acceleration and then asked what the mass is. But most of the problems, it'll be about here's a force, what's the acceleration? Or here's the acceleration, what's the force? Another very common use for Newton's second law is calculating the weight of an object. So the weight of an object, which is what we call the gravitational force, is equal to mg, where again g is what's called the gravitational acceleration, 9.8 meters per second. Whether you call this a gravitational force or a weight does not matter. Right? So again, a physical example where this stuff applies. Here I've got a picture of a car, and you'll notice the delta x's between snapshots are increasing. This is indicating that this car's velocity is getting bigger, which means we're accelerating. That means Newton's second law would be an appropriate thing to apply here. And if we knew the acceleration of the car, we could then calculate the force, assuming we know the mass. And if we knew the force on the car and the mass, we could calculate the acceleration. So it's a little bit about Newton's second law. Other laws to consider. I put this number 3 on my list here. I'm kind of doing this in order. Newton's first law and Newton's third law are also important part of Newton's laws of motion. So let me talk about the first one. And I'm using this arrow here to describe this. Newton's first law basically says you have to have a force, a net force on an object to change its velocity. It's worded a lot of different ways. If you read your textbook, it'll probably say an object in motion will stay in motion, an object in rest will stay at rest until acted upon by an external force. I like to try to condense that down a little bit. If you want to change an object's velocity, you have to have a net force. An example of that, this arrow. Imagine this bow in the fired position with somebody just holding it back. The velocity of that arrow would be 0. And that 0 is going to stay 0 until the string is released. Once the string is released, now the string will apply a force to the arrow in this direction. And that force will very quickly change the velocity of this arrow. So this velocity graph might look something like this. And when the bow is fired, it would jump right up pretty fast. So again, in this region here, that's where on the graph the force is applied. Now, as the arrow flies through the air, other than maybe some changes in vertical motion due to gravity, for now just consider it's horizontal motion. It will fly through the air at constant velocity, so the graph might look something like this, until the arrow hits something. Once the arrow hits something, there'll be a force on it, and the velocity will change very quickly, back to 0 presumably if it hits a relatively large object. So in this picture, there are forces applied here where the velocity changed very fast, and here where again the velocity changed very fast. So that's kind of an example of Newton's first law. Right. Newton's third law. I could use my arrow as an example of Newton's third law, but I chose to use this young girl here running with the puppy. So Newton's third law is that forces always appear in pairs, and sometimes I write mathematically F12 is equal to minus F21. And this is just a mathematical way of saying there's always going to be a force pair. The two forces are same magnitude, opposite direction. So for example, this dog, imagine this dog just peeling out and trying to run away from this girl as she follows behind. She is holding on, and that's going to apply a force to the dog in this direction. That might be, in this example, the F12. Simultaneously, there is a force applied here this way to the girl. That might be the F21. The minus sign example is, the minus sign is because these are in opposite directions, and they're equal in magnitude. So there's an example of Newton's third law. While I'm at it, I'll go through another one. If this dog is, trying to take off, and imagine the dog's feet just kind of digging into the ground, the force exerted on the ground would be maybe this way. Force exerted on the dog would be this way. Put F sub G and F sub D. And again, there's a force pair right there. Here's another example. We'll talk about the young lady here. As she's stepping on the ground, simultaneously there's a force upward on the girl. I'll put L for lady, because in the next picture I'm going to draw another one. There's also simultaneously a force downward on the ground. And I'm talking about the force interaction now right between her shoes and the ground. So these are all examples of Newton's third law. So at this point in the class, this is where I'm hoping everybody has some understanding of velocity graphs and how to use slope and area 2, how to apply Newton's second law. 3, conceptually understanding Newton's first law and Newton's third law about forces. So hope that this video helps kind of outline where we're at this point. Have a great day.